Alright, hello, welcome to today's mathematics class. And in this series, the course title is General Topology. And my name is Sondolu Afemgodogbe. I will be your instructor for this course. Alright, let's go. Alright, today we'll be checking the definitions of topology. So it's a very simple concept to understand, and you will surely find it interesting. All right, so definitions goes thus: let X be a non-empty set and tau a collection of subsets of X, then tau is a topology on X if it satisfies the following axioms. Okay, so the first axiom that will be satisfied is that set X, which is a non-empty set, and empty set also must be a member of tau. Also, axiom 2, and the union of any number of members of tau also belongs to tau. And lastly, axiom 3, the intersections of finite number of members of tau also belongs to tau. So these three conditions must be satisfied before we can conclude that tau is a topology on X. Alright, so let's check some examples in order to have a good understanding of this concept. Alright, let's check this example. Let S equals to set A, B, and we have tau 1, which equals to set X, empty set, and set A, and tau 2 is given as set X, empty set, set A, and set B, and we have tau 3, which is X and empty set. So we want to check which one of these tau is a topology on X. So we pick the first tau, which contain element X, empty set, and then set A. So first of all, check the axioms 1 that says that does tau 1 contain element X and empty set, and we can see that this is X, this is empty set, so they are members of tau 1. So that means that the first axiom is satisfied. Then the second axiom is to take the union of the members of tau 1 and see if the result also is a member in tau 1. Example now, we take X union empty set, and the result is X, and X is a member of tau 1. We also take X, we also take the union of X union A, and the result is X is also a member of tau 1. We also take empty set union A, the result is set A, which is also a member of tau 1. So that satisfies the second axioms. So then we check the third axioms, which is intersection of the member of the element in tau 1. So we check X intersection empty set, the result is empty set and is a member of tau 1. Also, we also check X intersection A, which gives us set A, and set A is also a member of tau 1. Then lastly, we check the intersection of empty set and A, which is empty set, and that gives us is also a member of tau 1. So we can conclude that since the three axioms are satisfied, then tau 1 is a topology on X. So the same thing on tau 2. At tau 2, we have the members of tau 2 to be X, empty set, set A, and set B. We check the first axioms. We can see that X and empty set are members of tau 2. Then that is first axiom satisfied. Then the second axiom, the union of this gives us X, which is a member of X. The union of these two is X, which also is a member. the union of this also is S, which is also a member of Tor 2. And also the union of empty set and A is A, which is also a member of Tor 2. The union of empty set and B is B, which is also a member of Tor 2. And the union of A, set A and set B is A, comma B, which is S, which is a member of Tor 2. As then that satisfies the second axioms. So we also check the third axioms, which is intersections of X and empty set is empty is a member of Tor 2. Intersection of X and set A is a member of Tor 2 likewise. And then the intersection of empty set and set A is empty is also a member of Tor 2. And then also the intersection of empty set and set B is empty, which is also a member of Tor 2. And then lastly, intersection of set A and B is empty, which is also a member of Tor 2. So since the three axioms are satisfied, then we can conclude that Tor 2 is a topology on X. Alright, so let's check the third Tor we have and see if it's also a topology on X. So the members of Tor 3 are set X and then empty set. So the first axiom satisfied, X and empty sets are members of Tor 3. And then the union of X and empty set is X, which is also a member of Tor 3. And lastly, the intersection is also in Tor 3. Then we can conclude that Tor 3 is a topology on X. Alright, so let me do a quick recap before we end today's lesson. Alright, again, the definitions of topology is X is a non-empty set and Tor is a topology on X if it satisfies these three axioms. So X, empty set belongs to Tor, and the union of any member of Tor also belongs to Tor. And lastly, intersections of finite number of members of Tor also belongs to Tor. Then if those three axioms are satisfied, we can conclude that Tor is a topology on X. Thank you. Meet in the next class.